So how exactly do you solve a mystery when a crime scene is, 40 million miles away, and your only clues are just faint radio signals and the few lines of code? Well, welcome to This Explainer. Today we're diving into one of the most incredible engineering detective stories in the entire history of space exploration. We're talking about the 1997 Mars Pathfinder mission. It faced two massive, near-catastrophic challenges, one during its fiery descent, and another while it was sitting safely right there on the Martian surface.
Here's the journey we've got ahead of us today. We'll look at two Martian mysteries, starting with the entry blackout and the physics of plasma. Then, we'll investigate the surface resets, crack open a priority inversion bug, and finally, look at the brilliant 40 million mile fix.
All right, let's jump straight into part one, two Martian mysteries.
Starting with our first major hurdle, the entry blackout.
Think of this whole thing like a high-stakes detective story, right? But the NASA engineers literally couldn't just walk over to the spacecraft and pop the hood to see what was wrong. Let's set the scene here. It's July 4th, 1997. The Pathfinder spacecraft is absolutely slamming into the Martian atmosphere at hypersonic speeds. The stakes are astronomically high, the whole world is watching, and then, nothing. The telemetry goes completely dark. For 30 terrifying seconds, that 8.4 gigahertz X-band communications link to Earth was just gone. Now, 30 seconds might not sound like much right now, but when a spacecraft is plummeting toward an alien planet, that is an absolute eternity. The team on the ground was just left waiting, sweating, and wondering what on earth just happened.
Which brings us to part 3, the physics of plasma.
To actually figure out what went wrong, engineers had to use aerothermodynamic modeling to look at the shock layer forming right in front of the spacecraft. When a vehicle hits an atmosphere at those kinds of insane speeds, the sheer heat literally tears the gas molecules apart. It creates this violent sheath of charged particles, basically a plasma. And this introduces our prime suspect, plasma frequency. See, if a radio signal's frequency falls below the critical plasma frequency of that sheath, the plasma acts like a giant electromagnetic shield. It just absorbs or reflects the signal outright. It simply cannot get through to Earth.
The math behind this blackout is actually pretty fascinating. You can see how the signal loss, or attenuation, spikes incredibly fast once the plasma hits a certain critical electron density. For Pathfinder's low-gain antenna, the modeling showed that the electron density blew right past the critical threshold for the X-band signal for about 20 seconds. And those remaining 10 seconds of silence? That was likely due to high Doppler dynamics and just a really low signal-to-noise ratio. But the core issue was that the plasma was physically blocking the spacecraft from calling home.
So the obvious question is, how do we stop this from happening on future missions? Well, the critical electron density you need to block a signal actually changes depending on which frequency band you're using. If you use UHF or S-band frequencies, it only takes a relatively low electron density to cause a blackout. But as you push up into higher frequencies, like the 8.4 GHz X-band or the 32 GHz Ka band, it takes a much denser plasma to block that signal. By figuring out these limits, engineers realized they could design future missions, like the Mars exploration rovers, to use specific frequencies that punch right through that plasma, totally eliminating the blackout period.
All right, moving on to part 4, the surface resets.
Okay, so the plasma fades, the parachute deploys perfectly, and Pathfinder totally sticks the landing. The Sojourner rover starts rolling around. Awesome, right? But just as the champagne corks are popping at JPL, a brand new, incredibly frustrating mystery pops up. The lander just starts randomly resetting itself, over and over. And every time it reboots, it kills an entire day's worth of science gathering. To understand why this was happening, we have to listen to Glenn Reeves, who is the flight software lead. He explained that this wasn't some busted hardware glitch, it was a software issue. Specifically, a notorious little thing called priority inversion, where, as he put it, a higher priority task was being blocked by a much lower priority task.
Let's lay out the software architecture here, kind of like a crime scene board. Pathfinder was running on a real-time operating system called vWorks. Inside, it had an information bus that acted as a shared data pathway. And activity on this bus was strictly scheduled on an 8 Hz boundary. Basically, everything had to happen in incredibly precise, tightly controlled cycles. Watching over all of this was a watchdog timer. You can think of the watchdog like a super strict security guard. If the high-priority tasks didn't finish on time, the watchdog just assumed something was catastrophically wrong, pulled the plug, and reset the whole system to try and save the spacecraft.
Which leads us straight into part 5, the priority inversion bug.
This right here is arguably the most famous concurrency bug in all of engineering history. It involves 3 specific tasks and 1 shared lock, which engineers call a mutex. Here is the exact fatal sequence of events step by step.
Step 1. A low-priority meteorological task, basically just gathering weather data, temporarily grabs the mutex lock, so it can publish its data. Step 2. The high-priority bus task wakes up, realizes it needs that exact same mutex, and politely goes to sleep to wait its turn. Step 3. A long-running medium-priority communications task wakes up and entirely preempts the weather task.
And this is where the disaster strikes. The high-priority bus task is waiting on the low-priority weather task to finish. But the weather task can't run because that medium-priority comms task is hogging all the CPU time. It's completely wild. The system's most important work is effectively running at its least important priority. Because the high-priority task is totally stuck, it misses its strict 8 Hz deadline, the watchdog timer wakes up, notices the bus management hasn't been executed, concludes the entire system is dangerously wedged, and boom, it triggers a total system reset.
So how do you fix a bug like that? Let's get into part 6, the 40 million mile fix. Back on Earth, the engineers were definitely sweating. I mean, they had a rover millions of miles away that was essentially stuck in a reboot loop. But thankfully, NASA practices the philosophy of test what you fly and fly what you test. They had actually left their detailed debugging trace logs enabled in the flight software. By running a physical replica right there in the JPL lab, they managed to reproduce the exact bug in just 18 hours. And the solution they found was a built-in operating system feature called priority inheritance. If you turn this on, a low-priority task holding a mutex temporarily inherits the priority level of the highest task waiting on it. In this case, that means the weather task would have been temporarily boosted, finished its job super quickly, and avoided being interrupted by the comms task altogether.
Okay, so they know the fix, but how do they actually implement it across the solar system? Well, the initialization parameter for that mutex lock was stored as a global variable in the spacecraft's memory. And because the operating system happened to have a built-in C language interpreter meant for debugging, the engineers were able to write a tiny, super short C program, blast it 40 million miles through the void of space, and change that single Boolean flag from false to true. And just like that, the resets completely stopped. The entire mission was saved by flipping a single bit. How cool is that?
Now, there are a few really vital engineering takeaways from this explainer that you should definitely keep in mind. First, always keep your debugging tools enabled in flight. Seriously, without those trace logs, Pathfinder would have been a total lost cause. Second, if you're using commercial off-the-shelf software, you absolutely have to understand exactly how it works under the hood. And finally, respect the watchdog timer. Those surface resets weren't actually the bug. The resets were the safety system doing its job perfectly, stepping in to prevent the spacecraft from operating with a corrupted information bus.
From tracing the intense physics of superheated plasma to debugging thread scheduling across millions of miles of empty space, the Pathfinder mission is just an incredible testament to human ingenuity. But, it also leaves us with a pretty humbling thought. As our spacecraft become exponentially more complex, and as we send them even deeper into the harsh, unforgiving environments of our solar system, what subtle, silent glitches are currently hiding in the code, just waiting for us as we push further into the cosmos?